In the previous video, we have learned about this special differentiation formula, and now we are going to learn on how to apply the formula into a real examination type of problems. Let's pick up some simple examples. Y equal to 4x cubed. So dy dx, which is the first derivative, is equal to, according to the formula, n multiplied with a. Now n is 3, a is 4. So 3 times 4, x to the power of 3 minus 1, which is equal to 12x squared. Alright, second one. Y equal to 2x squared. So dy dx. Alright, now 2 times 2 is 4. X to the power of what? 2 minus 1 is 1. So just leave it like that. Okay, it's very simple. Then, if you have something like this, then dy dx is, okay. Now x is to the power of what? X possibly is power of, not possibly, it's definitely is power of 1. So 1 multiplied with minus 5, then that's minus 5. And now x to the power of 1 minus 1, that equals to x to the power of 0. So what is x to the power of 0? X to the power of 0 is 1. Okay, whatever that power 0 is 1. So we can just ignore x, just leave it with minus 5. Lastly, y equal to 7. Then dy dx is equal to what? Now 7 with nothing there. So can we just imagine there is an x to the power of 0? Because x to the power of 0 is 1 anyway. So let's just put it there. And now just imagine that x power 0 is there. So according to the formula, then n is equal to 0. Then n needs to multiply with a, which is 7. Then 0 times 7 becomes what? Becomes 0. So 0 multiplied with whatever that remaining of x to the power of minus 1 is basically 0. So the final answer is 0. It's nothing. Okay, these are 4 very simple problems. But what if we have all these 4 terms combined into a single polynomial? For example, let's put it this way. Y equal to 4x cubed plus 2x squared minus 5x plus 7. So they are basically, I'm just adding all these 4 terms that we have done in the first, for example, and put it into one single polynomials. So what is a dy dx? Then dy dx is exactly the differentiation of each single terms inside that equation. So that is equal to d dx of 4x cubed plus d dx of 2x squared plus d dx of minus 5x plus d dx 7. Alright, now probably you are seeing something that is new. This term here, d dx. Where is the y? Y is not there. Why is that? Well, because whatever that's inside the bracket right after that is y. For example, 4x cubed, right? Why? Because y is 4x cubed. Then dy dx is equal to d over dx of 4x cubed. Okay? So that is just another convention of writing the first derivative or differentiation of a term. So let's continue. The dy dx for this 4x cubed is as we have done in the first example earlier, which is 12x squared plus 4x minus 5 and plus 0. Then we forget about it. So that's the answer. This is what we call addition or subtraction rule. Okay, so let's try to use another of that addition and subtraction rule. Let's do a slightly more complicated example. Y equal to 2x squared minus x plus 1 over x. Okay, this is new, right? Minus 3 over x squared plus 3. So what is dy dx? Dy dx is the differentiation of each single terms inside it. So 2x squared, what is the differentiation of 2x squared? Equal to 4x. What about minus x? Minus x, differentiation is minus 1. Okay, now, what is 1 over x? Let's put it here. D dx of 1 over x is equal to d dx of x to the power of minus 1. Imagine there's a 1 here because x is just actually x minus x to the power of 1. Okay? If we put it into the numerator, then plus 1 becomes minus 1. So in this case, it is differentiation of x to the power of minus 1. So what is differentiation of x to the power of minus 1? That is equal to minus 1x minus 2. So because this is minus 1, 1 can be just disappear. We don't really need to show it. So minus x to the power of minus 2. And what about this one? The same. Okay, identical to the first situation. That is equal to 3 d dy 3x minus 2, which is minus 6 minus 3. Alright, minus 6 minus 3 plus 3. Okay, and we can make it nicer. This is accepted, but we can make the equation, the expression for dy dx a little bit nicer by doing this. Put back all the numerators, the negative the power numerator to positive. I made a mistake here. There is no plus 3 here. Alright, because differentiation of 3 is 0. This is the final answer. Another example. The last example, I'm going to put it into a function format like this. Fx is equal to 3x cubed minus 5x squared plus 2x minus 3, everything over x squared. Okay, so how do we perform differentiation? We are not going to use dy dx here. Why? Because variable y is non-existent in the third example. So we need to have a new representation of first derivative for function like this. So first of all, let's divide all the terms in the function with x squared. So that is x fx equal to 3x cubed divided by x squared, that is going to be 3x, minus 5x squared divided by x squared is equal to minus 5, and 2x divided by x squared, that is equal to 2x to the minus 1, and then minus 3x to the minus 2. We need to have a new format to write the first derivative of fx. So the way to put it is to add a symbol prime here. So this is the derivative function. So f prime x is equal to 3 minus 5, derive it to become 0, and minus 1 and 2 is minus 2x minus 2, and this is plus 6x minus 3. So that is equal to 3 minus 2 over x squared plus 6 over x cubed. Okay, this is acceptable. Well, this looks a little nicer because we have turned the negative power into a positive power. So now is the time for us to go a little further. Let's try to use all the knowledge that we have learned this far to solve some more complex issues, more complex problems. The one that is much closer to the examination questions. Okay, shall we?